All right, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 341 Power Systems class. Today is our 24th lecture, and can you guys hear me well? All right, thank you, Eamon. And here I'm sharing the Gantt chart. We're at this very cell right here, and so. Since we missed the one lecture, so today is actually our very last lecture of Module 6. And after today's lecture, we have the very last quiz to do. Don't forget that. Okay. And let's now begin with reviewing the basics of the medium line model. Okay. Medium line model. Let's review some basics. And since the algebra calculation, I don't know if you have realized, is actually extensive. It's quite intensive, actually. So the model is fairly easy. Just we have a series impedance and two not parallel but shunt admittance. Okay, so we call it Z. This is half Y and half Y. This is the model we have. Okay, and we have this sending end voltage and the current, and the receiving end voltage and current. And one thing, first thing you need to be very careful is all of these voltage and currents are phase quantities. Okay, phase voltage, phase current, and this is of course also the per phase circuit model. Right. So this is very important. Okay, so everything in our equation formulas are actually in terms of phase quantities, not line ones. And further, we derive the sending end voltage and current, of course, phase voltage and phase current equals to matrix 2 by 2 times the receiving end voltage and current. Okay. And of course, if needed, we can also derive the other way around. Okay. Right. Pretty much these metrics are the inverse metrics of this guy, right? Very straightforward, very straightforward. And the key is make sure you are copying the correct equation for A, B, C, D. Okay. A is what? 1 plus Z times Y divided by 2. D is equals to A. B is fairly easy, Z itself. C is Y times 1 plus Z times Y divided by 4. Okay. And make sure you are having the correct equation here. Of course, here, anyone remember Z is what? Y is what? Anyone remember?
G is impedance and Y is admittance.
Correct. That's correct. And in terms of the equation formula, then Z equals to what?
That would be the line impedance, and then Y is the admittance of the capacitance.
That's correct as well. So specifically, is this, right? And then admittance, So pretty much over, right? Of course, here, don't forget to times what? What is it in red?
The length of the transmission line.
Good. Yep, the length of the transmission line. Okay. And because the parentheses here, all of these are the per unit length. Okay, the value per unit length. And of course, here the XC, a little bit more here. C equals to negative J over omega C, right? Negative G omega C. Right? So be very careful how to calculate them. Okay, how could you calculate them? Because in the quiz or exam, following certain order, you want to calculate Z and Y first, right? After having Z and Y, you go ahead for A, B, C, D. After having A, B, C, D, you go ahead for VS or IS, right? So ZY goes first. The ZY goes first. ZY goes first. Make sure you follow such order. And then, of course, we also have equations for voltage regulation, right? Voltage regulation. We are no load magnitude. The magnitude, okay, be very, very careful. It's because the VR definition is consistent and the same, okay, identical for both medium line or short line. So you don't want to miss. Right? Magnitude, okay. Now remember this magnitude. Okay, it's not the voltage in phasor. It's the magnitude of it. Okay. The VR value here is a constant value. It couldn't be phasor. It couldn't be a phasor. However, it could be what? Positive or negative. Could be either way. Okay. The sign could be negative. That's absolutely possible. Okay. The sign is negative. Absolutely possible. The negative sign means what? Anyway, remember which example we actually had negative VR. And what does it mean then? Anyone remember? Anyone, any impression? So first of all, negative VR means what? Numerator here is negative, right? Which means the full load receiving end voltage is greater than the no load receiving end voltage. This means what? After loading, the voltage becomes more, right? What could make this happen? Anyone still remember? Yeah, basically Sawyer is right. It's not too much capacitance. It's too much capacitive load, right? It's all up to what kind of load you're loading your voltage, right? You're feeding your voltage up, right? So it's up to what types of load, inductive or capacitive. Okay. You are feeding capacitive load. That's absolutely the resultant voltage is actually increased. It's absolutely possible. And this is also you recalling in the power system, we always need a capacitor bank, right? A capacitor bank. The capacitor bank is essentially for what? For providing the reactive power to the transmission line. Why you need the reactive power compensation? That is also called a reactive power compensation. Why you need it? Because you're feeding certain load and then you're losing reactive power. Losing reactive power, your voltage can drop. To hold this voltage back up, you need to compensate the reactive power. Okay, this is very regular action in the power system control room. Okay, that's why you're gonna see a lot of capacitive load, the capacitor bank, trying to compensate the reactive power, because the majority of the load is inductive. Okay? Inductive load is gonna reduce your transmission line voltage. Okay, so compensating that by capacitor bank. Have you guys ever seen or ever done anything like ever seen like the capacitive load or anyone here is working for consumer energy? You should know that better. And this is the voltage regulation. And the last one we need to take care is the efficiency. Efficiency is the ratio between two powers. So who is the numerator and who is the denominator? This is also very important. Very easy to make mistake. But what is the numerator here? Right, numerator is the P, denominator is P as well, right? And the numerator is the receiving end, P. Denominator is sending end, P. Okay. So the key is the active power and active power only. Okay. It's not S. Only reactive power, which is the real number. Real number, and then resulting in a constant efficiency here. So your efficiency won't be a phasor either, for the same reason. And if these are clear, and then let's maybe go over this example for medium line transmission line model. This example is given like this, that the transmission line length is given. Of course, we need it, and not only for times the length, okay, but also you need to judge which model you should apply. Okay, be very careful. This transmission line length, it matters a lot, and also the frequency you need it. Okay, what the frequency is for? What are you expecting? Impedance, okay, impedance, okay, and specifically is reactance, right? You're gonna need it to calculate the reactance, okay? So this is something to find omega, and omega to find reactance X. You should have such expectation. Then when you read the problem, you won't miss any information, okay? This frequency is 4, and then per phase parameters included lowercase r, capital L, and capital C. So resistance, inductance, and the capacitance. per unit length, per unit length, per kilometers, okay, per kilometers. And then it's telling you receiving end voltage is 3 to 5 kilovolt. So first of all, you need to understand this 3 to 5 volt is a given. Receiving end voltage is line voltage. Okay, this need to be very careful. Very careful. It's line voltage. It's line voltage. And if the system is the Y-connected system, you know, to find VR phase voltage, you need to divide by square root 3. Okay, be very careful. The given voltage here is line voltage. What you need is phase. Okay. The second thing you need to be very careful is also we are giving the phase voltage VR 0 degree phase angle. So reference 0 degree is the receiving end voltage, phase voltage, okay, rather than sending end voltage. Okay. This VR has 0 degree, not VS. Okay, this is the second thing you need to be careful. And then move on, and also giving you the power at load, the power at load, or say the receiving end power, 270 mega VA. Well, this guy you need to be careful. This is, first of all, is a magnitude. This is not phasor, not yet. Okay, it's the magnitude, 270 mega VA. According to the unit VA, this is something we also learned from previous module. According to the units, this is S rather than P, rather than Q. Okay, so the unit is telling you that information. The 270 mega is the magnitude of the S for receiving end. Okay. And then what you need is obviously the phasor, right? The magnitude itself is not enough. So you have to find the phase angle so that you can find the phasor of SR. You have to use the given power factor, right? Given power factor. This is the information. These are the information given, and then find, not a surprise, VS, IS, VR, and efficiency. And in the calculation, as I said, the first step is find Z and Y. Okay, capital Z impedance and capital Y admittance. Z is due to the resistance and the inductance, and the Y is due to the capacitance. And here are the calculation in details. Be very careful. Sometimes this is given in what? Millihenry. Milli. That's 10 to the negative 3 matters. Okay, that's absolutely matter. That absolutely matter. And the capacitance here might be also what? Micro, right? Microfarad. All of these need to be taken into account, okay, in your calculation. Otherwise, absolutely no chance to be right. Okay, because the algebra here is, yes, is quite intensive. Okay, it's quite intensive. Is after having Z and Y, you need to go for A through D. Okay, algebra again. And after having A through D, you go ahead. Try to find the VS and IS. And what you're seeing is, you know, A, B, C, D. VR is also identified as the line given line voltage divided square root 3 with angle of 0, right? And then you need IR. How to find IR? IR is derived out of this SR. SR equals to 3 times VR times IR conjugate, so you can find IR. Right? You have IR, VR, A through D. Then you can find VS and IS as this. And the VR is equals to VR no load minus VR full load divided by VR full load. Be very careful to given VR, or say the or say the 325 divided by square 3 kilovolt. This is the full load voltage, okay? The problem is telling you 325, right? This line voltage, and then you can find VR, and this VR is nothing but VR full load. Does it make sense? This is not the VR no load. This is VR full load voltage. Okay. This is something you need to be clear as well. Okay. Therefore, this is easy. How to find the VR no load then? Anyone remember how we find the VR no load?
It was VS divided by A.
Correct.
Magnitude. Yeah.
Very good. Okay, VS divided by A. Okay. Of course, magnitude of it to be used in this equation, right? VS divided by A. And then we got VR voltage regulation, 7.28%. And the last to find the efficiency. Efficiency is, once again, you need PR and PS. How to find PR and PS? Be careful, okay? How to find PR and PS? You need to find SR and ISS. And then the real part of them are respectively PR and PS. Okay, this is how you find PR and PS. Based on the SR and SS. Okay, this is the procedure. This is the correct procedure. Active power, reactive power, and apparent power. Okay, you need to be very clear about the relationship among them. Okay. Real part of the S is P. Okay, just simple like that. And then you can find the efficiency here. Of course, when you check this, your efficiency should less or equal than unity, right? If you find the efficiency is as high as 200%, and it's definitely wrong, but you need to see how much time left to go back, right? In the exam, if you do have time to go back, and then you need to go back. Okay, you need to go back because 200% is no way to be right. So this is the we pretty much go over the procedure to solving a medium line model problem. It's quite involved. Okay, involving, for example, the basic power relation. And involving quite a bit impedance admittance calculations. Okay, not very straightforward. It takes time. It takes time. Okay, you will see that from our quiz 3 as well. Right? But the procedure, the logic should be clear. Should be clear. Okay, not very difficult in terms of those. Anyway, any questions? Any questions regarding this part? All right, if these are fine, then we gonna move on to talk a little bit about the long line model. Of course, it does exist. Well, no one is leaving the lecture. That's good. first of all, you still need to be clear about the boundary, right? So what is the boundary? Longer than what?
250.
250 kilometers. Okay, 250, correct. Okay, correct. 250. Okay, 250. And of course, we are expecting to see a more complicated model, but actually the basic look remains same as the medium line model. Basic parameters like these voltage and the current remain same as well. Then what's the difference? Well, first, this is called pi model. If you by any chance read any literatures, actually, you will see this name, pi model, pi transmission line model. Okay, pi. Why it is called pi model? Anyone can see why it is called pi model? It's the kind of a tricky question, okay? Because it looks like
pi?
That's right. Okay, it's about the look. Okay, it's about the look. Yeah, there's no logical reason. It's just a very very straightforward. The look is pi. Okay, the look is pi. Okay, the look is pi. Pi, right? Anyways, this is not important. What matter is the parameters here. So first here, this series impedance is not simple repeatance, but is Z sub C times sine hyperbolic function of gamma times L. What is this? You guys ever learned this? Hyperbolic function? Have you guys learned this before? Whoops. Little bit better. Think so. Yeah. Not much. Not intensively. It's we actually not often using the hyperbolic function, but I can give a little bit background about it. The hyperbolic function is actually mathematically. That's just a we won't go deep either. But I just introduce maybe two very basic, three maybe very basic hyperbolic functions. They're equals to what? It's actually it equals to this. Okay, mathematically they equals to this. Okay, it's in terms of exponential function. I think we just stop here and move on to our model. So you can tell the series impedance here is not as simple as Z, but a Z sub C times hyperbolic function of gamma times L. Obviously, we don't know gamma and Z sub C either, and we will introduce that later. Okay, and the shunt admittance here is not simply capacitance either. Okay, it's actually this. It's 1 over Z sub C times tangent hyperbolic gamma times L divided by 2. Okay. And same thing here. Okay. These two shunt admittance are same. And here, let's introduce what it means by, first of all, a gamma. Gamma is what? Equals to square root of Z times what? Z is what? Y is what? Z is, well, finally, right? Finally, we are seeing something we understand. Now this guy Z is the what? The impedance per unit length. This is admittance per unit length. A little bit of review. So this guy is what? This guy is what? Inductance. Good. This guy is what? Capacitance. Right. This guy is what? Reactance. Good. This guy is what? A little bit hard, but capacitance, reactance. No. It's not capacitance, reactance. It's what? Reciprocal of it, right? Which is what? Susceptance, right? Susceptance, right? And this is resistance, you know. Resistance. What is this guy then? Anyone remember what is this guy? Conductance. Here we go. Yes, good. So this is the impedance, and this is the admittance. Okay. So the product between the impedance and admittance and square root of the product is equal to gamma. See how complicated it is, right? And this gamma, don't forget to times the what? What is this? Length, transmission line. And then you receive the total gamma. And then sine hyperbolic of it times ZC, which we don't know yet. ZC is what? ZC is equal to square root of Z over Y. Okay, here. So after figuring out the gamma and the ZC, we basically have the full picture of this model. And second here is 1 over the ZC times tangent hyperbolic of the gamma times the length divided by 2. Well, it's complicated algebra. However, the logic and the reasoning is not that bad. It's not hard. Okay. So, and also we are seeing what? We are seeing the long line model include the effect from every single thing. What? Series resistance, series inductance, shunt conductance, and shunt capacitance. Include every single what we call it, elements we ever learned before. Okay, it's a long line model. It's quite complicated, complicated. And of course, based on these basics, we are going to derive also. We are also going to have this. Okay. It's not hard to imagine. There's also a matrix which is at least looks not that bad, right? 2 by 2. I mean, 2 by 2. And when you have 2 by 2, however, the tricky thing is A, B, C, D are different from the A, B, C, D of the medium line model, right? A this time is cosine hyperbolic gamma times L. B is Z sub C times sine hyperbolic of gamma times L. C is equals to 1 over Z C times sine hyperbolic gamma and L. D is equals to A. So these are the basic equations or relations for us to derive anything more. VR remain same, efficiency definition remains same, right? All of these obviously, and no reason to change. Okay. So you have VS, IS, VR, and efficiency. Right. Any questions regarding the transmission line? Basically, we are done here for this module. Any questions? Anything you want to discuss? Here, well, why not just speak it out? You spend so much time on typing. We talked a lot about carrying power in transmission lines, but these elements are the same for sending information, right? These elements are the same for sending information. Oh, not quite following this question. What do you mean by these elements? These elements, you mean the RLGC, right? Sending data along transmission. Oh, these parameters are constant. Yes, these parameters are constant. The length is involved into, or say, kicking to the picture by here. You see, we always have length involved. Yeah, the parameters, yes, the constant. We consider them the constant. The effect from length is playing role by here, like times the length. Right? That's right. That's right. And the in the control room of the consumer energy. Of course, they have a computer to carry out all of the complicated calculations and then come up with the decision options for the engineer to click. All right. I think that's all for this module. I plan to move forward for the very last module, but I think we can have a short lecture today. So before calling an end, any questions regarding the quiz or this course overall? Any concerns? Of course, remember, okay, whenever you have time, remember to review the three-phase power knowledge, because one problem gonna be in the very last exam for sure. Okay, we had this deal long time ago. Okay, so it remains valid. Okay. Any questions regarding the course, regarding the say the grading or anything you have concern about? Well, here, Gavin is asking, will the quiz be available right when this class is done? If I get out earlier, no, it's set to be 5:30. Okay, it's set to be available from 5:30 today. Let me take a look. Okay, let me make sure it is. Let me make sure it is quiz 3. Yeah, available from today 5:30. Due by tomorrow 5:30. 24 hours. Any other questions regarding this course? Any thoughts? Any questions regarding, say, grading or the timeline? Anything? Next Monday, a week from today, I'm gonna review the very last exam. Okay. So next Monday lecture, I'm gonna do the review. Anything else in your mind? Oh, by the way, this long line model, I'm not planning to put it into quiz or define last exam in format of calculation problem. However, I might ask one or maybe two questions in the multiple choice. That's possible though. Okay, so some basic concepts you still need to understand. All right, I think that's all from me. And if no questions, I call it end. All right, thank you for attending today's short lecture, and talk to you guys on Wednesday, when we gonna start the very last module. Okay. All right, thank you. Bye.